Now it's time to solve our exponential equations. So we're going to look at several different ways. To start with, we're going to look at our common bases. Recall that whenever you look at your exponential function, you have a base and you have an exponent, right? Usually our exponent is x, and we'll be solving for that exponent. So when you solve with like bases, if the bases are equal, then the exponents must be equal and vice versa. For example, if I said 2 to the x equals 2 squared, because these are both 2, that means that this x over here has to be equal to 2. There's no way 2 to any other power would equal 2 squared. So for the first example, I've got 7 to the x minus 1 equals 49. Well, I know that I can rewrite 49 as 7 squared. And then because I have the same bases, I don't need them anymore, and I can write an equation that says x minus 1 equals 2. Then to solve for x, we add 1 to both sides, and we get x equals 3. And I can plug it back in and check. 3 minus 1 is 2, 7 squared is 49. So you're always looking to see that you can rewrite. This is one of the easier ways of solving exponential. So if you can rewrite a base or rewrite a number with the same base, that's the route you want to take. So example 2, I've got 16 and 8. And 8 does go into 16, but not 8 to a power, because 8 to the first power is 8, and then 8 squared jumps to 64. So my base is an 8. 4 also goes into these two numbers, and 4 squared gives us 16, but 4 to the first is 4, so we skip over 8. So 4 can't be our base either, so if we keep getting smaller. 2, alright, so if I look at 2, 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8, and then one more 2 gives us 16. So I can take 2 and go to an exponent to get 8 and 16. So I'm going to rewrite 16 as 2 to the fourth power. And I'm going to rewrite 8 as 2 to the third power. Now it's important to keep these in parentheses. And now my exponent rule says that if I have a parentheses between my two numbers, I multiply. So I get 2 to the 4x equals, and then over here I've got to multiply, which means I distribute. So it equals 2 to the 3x minus 3. Don't need my bases anymore because they're the same. So we have 4x equals 3x minus 3. Subtract my 3x from both sides. X equals negative 3. Our third example looks a little different. I've got a fraction. Don't let the fraction freak you out. Just remember, if I have, for example, 2 to the negative first power, to get rid of that negative, I rewrite it as 1 over 2 to the positive first, which is just 1/2. So you have to flip your fraction to get rid of that negative exponent. So with that being said, anytime you see a fraction, you have to be working with a negative exponent. So if I start, I might say 9 to the negative 1 equals 27 squared. Right, or 9 to the negative 1 times x. Right, I know it's got to be a negative. But again, 9 does go into 27, but not 9 to a power, because 9 to the first is 9, and 9 squared jumps up to 81. So I've got to go smaller. So I'm going to look at 3. 3 to the first power is 3. 3 squared is 9, and 3 cubed is 27. So I'm going to use my base of 3. And then just remember, because this is a fraction, it's not going to be 3 squared, it's going to be 3 to the negative 2, so that I get that 1 over 9. And then over here we're going to plug in 3 cubed. Again, I have to multiply, so we get 3 to the negative 2x equals 3 to the 6th. I don't need the 3's anymore. Negative 2x equals 6 divided by negative 2. X equals negative 3 again, just like the last example. So that's solving using your common bases. We're also going to look at solving using a calculator, right? Sorry about all my things being off here. But, for example, if I said my equation is 2 to the x equals 9. I can't rewrite 9 with a base of 2. So I cannot solve this using like terms. But what I can do is type it in my calculator. And everything shifted over here. So that's going to be in y1. This is going to be in, oops, can't move that. This is going to be in y2. So if I pull up my calculator, I'm going to turn it on, go to y equals, and in y1 type in whatever's on the left side of my equation. So 2 caret x, and then on the right side I put that in y2. Then when I look at my graph, I'm going to get an exponential curve as well as a horizontal line. And my answer is where they intersect, because this just became a system. So to find the intersection, we're going to go second trace, intersect. And if I've only got one intersection, I'm just going to press enter, enter, enter. So my y value is 9, because that's what I typed in. So my x value is what I'm looking for, and we get 3.2. So my answer here would be x equals 3.2. So left side in y1, right side in y2, find your intersection, and the x value is your answer. Alright, so for this example, I can rewrite 4 as 2 squared, but I can't do that for 12. So I'm going to put this in y1 and 12 in y2. So I have 4 to the x and then a 12. I'm going to go to my graph. Now in this case, because I'm using 12, 12 is going to be up here out of my window. Alright, so I'm going to just zoom out so that I can see that intersection. So there's my exponential curve. Here's my horizontal line. I don't actually have to be able to see it clearly as long as it's in my window. So I'm going to go second trace, intersect, enter, enter, enter. And x equals 1.8. And our third way that we're going to solve is using what we call logarithms, which we're going to do a lot more with. But our logarithm is kind of like the inverse of an exponential. They cancel each other out. Alright, and one of our properties of a logarithm is that we can rewrite a logarithm and an exponential, like vice versa. So the way we do that, it is always log base b, right, and that's that same base in our exponential. So log base b of y equals x is the same as b of the x equals y. So the way that we do this is we go around the world. So you always start with your base for your logarithm, and then you go around, so it's going to be b to the x equals y. So b to the x equals y. Same thing when you're writing it back in logarithm form. You start with your base, go around the world, and back. So then it's log of base b of y equals x. So you're going around the world every time. And the main thing that we use with these logarithms is this power property that says if I have a log of 4 to the x, I can take my exponent and put it out front, and it becomes x times log of 4. And that's going to help me because I'm taking my exponent that I'm trying to solve for, and I'm getting it out of the exponent. So then I can solve like normal. Okay? One thing to keep in mind, all we're doing right now is what we call log base 10. That's going to help us solve these. That's what the calculator uses. And so in our calculator, we have a button right here to the left of 7. That's log. So as long as we're in log base 10, which is what we're going to use right now to solve, we can just plug it into our calculator. Alright? So for our first example here, I've got 2 to the 3x equals 7. 2 and 7, there's no way I can write those as the same base. So I'm just going to take what we call the log of both sides. And remember, whatever you do to one side, you have to do to the other. So now I've got log of 2 to the 3x equals log of 7. Alright, now power property says I can take that 3x and put it out front. Alright, this value here, log of 2, that's a number. I can type that into my calculator, log of 2, and it's an irrational number, but it's a number. So that's just like 5. Alright, so we have 3 times x times this number, 0.30102, blah, blah, blah. And I want to get x by itself. So I can start by getting rid of that log. So then I've got 3 times x, and I'm just going to leave it. We're going to plug it in at the very end. And then I got to divide by 3. Alright, so now I'm just going to type it into my calculator. So I'm going to start with log of 7. Now notice when you type log, a parenthesis opens. I have to close that parenthesis because I just want log of 7. That's all I want in there. Divided by log of 2. All right, and I'm going to go ahead and press enter. Take that number and divide it by 3. So then my x equals 0.94. Okay, we just take a log of both sides and use that power property to get our exponent down, and then we solve like a normal equation. Okay, so for another example, I've got 3 times 5 to the x plus 2 equals 18. Okay, I'm going to start like we did with our absolute value and our square roots and all of that by getting this base to the exponent by itself. So I want to get rid of this 3. So I'm going to divide by 3. So I've got 5 to the x plus 2 equals 6. They don't have a common base, so I'm going to take my log of both sides and just rewrite it. So we got log of 5 to the x plus 2 equals 6. My exponent can come out front. So I've got x plus 2, and I'm going to leave it in parentheses, times log of 5 equals log of 6. Remember, log of 5, that's a number value. That's just like 7 or 10 or any other number. So I want to slowly get x by itself. So I'm going to start by dividing by log of 5. So then I get x plus 2 equals log of 6 divided by log of 5. Again, I'm going to wait and just plug it all in the calculator at one time. And then I want to subtract 2 from both sides. Alright, so then in my calculator, I'm going to do log of 6 divided by log of 5, and then subtract 2. So I got log of 6, close your parentheses, divided by log of 5. Alright, it's a good habit to go ahead and close it. And then I'm going to take that minus 2. So I get negative 0.89. Alright, so our 3 options for solving. First, in the easier option, common base. But not everything's going to have a common base. So then we have 2 options. Another one is a calculator. Right? And you basically create a system. So the left side goes in y1, the right side goes in y2. Find your intersection. And then our third option is using what we call logarithms, where we take the log of both sides, because whatever you do to one side, you have to do to the other. And then we use our power property, and then we solve for x and plug it into the calculator.